Okay, I'm working from home as well today. What we're working on, I'm doing it because we've been asked to check our internet connection. Mine is a little bit shaky. That's why I'm preparing a quick video for you to learn from. What we're going to be learning today is about surd form of numbers. And surd form is a way of representing numbers exactly, often involving a square root. If you're looking for these in Khan Academy refers to them as radicals because that's the American name. Now, the reason we need these is, like I said, they represent numbers exactly. And what I've put in this little diagram is all the ways that sets of numbers that we know and we can represent in an exact form. So we've got things like natural numbers, 1, 2, 3, 4. They're simple counting numbers. Sometimes this includes 0. Integers are positive and negative counting numbers, including 0. And they then can also be represented as a fraction. So any number that can be represented exactly as a fraction is rational. So we're talking about halves, quarters, 3/4. 3,726 divided by over 14,732. That would be a rational number. Then beyond those, we've got the real numbers. There's two groups inside the real numbers that you need to be aware of. One is the Transcendentals. They're special numbers that can't be described in terms of something else. They are almost a fundamental constant of the universe. They are a fundamental constant of mathematics, which is why people like what's called the Euler expression, which is e to the I pi plus 1 equals 0. Because that expression contains all the key elements in mathematics. We've got the Euler's number, which is e, and it's got a special property that the value of e to the x is also the gradient of the line at that point. I is complex numbers, which is a set beyond these. Pi, circumference of a circle divided by the diameter. 1 is the multiplicative identity. So if you multiply by 1, it's the thing that doesn't change it. 0 is the additive identity when you add 0 to anything. They are fundamental constants of mathematics, and that's why Euler's expression is loved by mathematicians. The ones we're looking at today, though, are the algebraic numbers called surds. And they are, the reason they're called algebraic is their solution to what are called polynomial equations. So things like x squared is 2 or x to the 4 is 9. Okay, so that leads to the 4th root of 9, which gives us x is plus or minus the square root of 3. And these numbers, they can't, actually the algebraic should include the rational numbers. So that is actually a superset of the rationals, because rational numbers are algebraic numbers as well. So a slight mistake in my diagram. So we're actually talking about finding solutions to these, particularly giving exact answers. So I've got a few examples over here of simplifying simple ones. So to start with, let's just do the square root of 9. Square root of 9 is the same as the square root of which number do I repeat? 9 is a repeated multiplier of 3, so the square root of 9 is one of those 3's. As this says, take half of these numbers. So if I now move on to square root of 18, what I need is I can break it out into, are there any numbers that I know pair off? Well, an easy way is to do prime factor decomposition. So we write it in its prime factors. Look for the repeated value that we can take out. So I can take out a 3. But this square root of 2 I can't do anything with. So that square root of 2 needs to become stay in my expression. So it's a bit like having a variable that you can't change into another one. So it's a slightly different part of the number. So this is now 3 times the square root of 2. It's the same as the square root of 18. Let's go for the 175. So 175 is going to be the square root of 5 5's 25. And 25 times 7 gives me 175. So 5 5's, I can take out one of the 5's, and I can have the square root of 7 left on the outside. That number is an exact answer. If you're not familiar with, or just to remind you, the way to find prime factors, say 45, you can think of any multiplication sum, so that's going to be 5 times 9. 5 is prime, so leave it. 9 can be split into 3, 3, and they're both primes. Or you can try doing the 5 prime trees. So can you do it? Divide by 2? No. Can we divide that by 3? Yes. So 3 into that goes 1, 5. Can that divide by 3 still? Yeah. So we keep going with the same prime number until I can't go any further. So 3 doesn't go into 5. What's the next number to try? 5. 5 into 5 goes once, and that's the stop. So any number I've got here that's got a number next to it is my prime factors. So we want 3, 3, and 5. That's 2 ways of doing prime factor decomposition. Okay, so if you haven't remembered those. Let's move on to the next level then. So we can step these up, and we've got things like, what happens if we do the square root of 4 times the square root of 16? Well, let's write it in a single bracket, square root sign first. Notice square root's not, you can't do anything if this one of these is a cube and this one's a fourth. They must be the same power. So I'm going to do a square root. 4 times 16 is 64. I know 64 is 8 times 8. So I can do that one by the value of 8. I didn't need to do prime factor decomposition. If you can recognize a pairing that works, you can use it. We didn't do one of them. No, that's a number 5. Let's have a look at the square root of 15 times the square root. Oh yeah, I did do it over there. So square root of 3 gives me the square root of 45. Square root of 45 we know is the square root of 3 times 5 from that technique. That gives me a 3 outside and a square root of 5 left. Okay. So if I wanted to check that one over here, I can put in 3 is my number, press the square root button, and 5. And I'll check it. It came out as correct. Next sort of question. So that's, if you want to separate these out, I would suggest maybe do a section. So that's level 1. That's level 2. And let's look for level 3. So 3, this is where they're going to start combining things together. Let's look for that one first. So number 6, we have 2 times the square root of 7 multiplied by 5 times the square root of 12. Well, deal with the integer parts together. So the 2 times 5, they come together. And that gives me 10. And the square root parts, we've got to do the square rooting part. So 7 times 12 is 84. Off the top of my head, I don't know what 84 is, so let's do prime factor decomposition. I know it will divide by 4. So we get 2 and 2. 4 times 21. 21 is 3 and 7. So now I've got some numbers I can take out. 10 times the square root of 2 times 2 times 3 times 7. This is equal to, take the 2 out, so I've now got 2 times 10 is 20. And the 3 times the 7 is 21. So 20 times the square root of 21. There's my surd form. Some of these here, they've got other bits going on. Let's have a look at that 4 third root. A little clue for you, because there's no third root button here and you can't put a 3 in front of the square root, you know this is going to disappear. So for the third root of 2, all cubed. Distribute the power over the 2 sections. So we've got 4 to the power of 3 times the third root of 2 to the power of 3. And just a little thought about our indices. 2 to the root 3 is 1/3. So we're doing 1/3 to the power of 3. Multiply those two and we get 2 to the 3 over 3, which gives me 2. So we've now got 4 cubed, which is 64, times 2 from that part, which is 128. Put the number in and check it. Okay, level 4. I think the level 4s is the adds and subtracts. There we go. So it's just putting them up. So these are adds and subtracts now. And what you need to be able to do with this is get both of these so that they've got the same square roots going on. So level 4. So with the level 4, let's go for 1248. Now you're looking for one of these to be the same. It's a bit like dealing with fractions. Well, I know this is 4 times 12. So what I have is the square root of 12 plus, take the square root of 4 out and the square root of 12. And this gives me root 12 plus 2 root 12. Hopefully some of you will spot this, but just in case you haven't, if I was to replace this with a variable, say t for 12, I've got t plus 2t, which is 3t. Okay, so I now have 3 times the square root of 12. Let's go for the bottom one, that one. So number 9, I'm doing 20 root 5 plus or minus 5 root 20. The focus is on what's inside the root sign. So I'm just going to scroll this a fair way up because I'm writing at the bottom of the tablet, which is partly why my writing's so bad. So I've got 20 square root 5. I want to write this in the form of something times the square root of 5. Well, 5 times 4 gives me the square root of 20. So we're going to subtract from this 5 times the square root of 4 square root of 5. Square root of 4 is 2, so we've got 20 minus 2 times 5 is 10. Oops. Square root of 5, so 5 times 2 is 10, sorry. So we've got 10 square root 5. That was level 4. Level 5, dealing with divisions. Now, divisions you might find it easier if you do the division inside a single one. So you can do it in two ways. Let's go for square root of 216 divided by the square root of 6. You could try factorising them out or finding a square root, or this distributes across a division as well. So we've got 216 divided by 6, which when you divide through, 6 goes into 21 3 times, with 3 left over. 6 into 36 goes 6 times. Square root of 36, I know, is 6. And nearly all of these will do something similar. So that's the level 5. Level 6, you've got the numbers in front, so that's level 5 and level 6. So you might want to just go into level 6 rather than doing level 5. And yeah, we'll deal with that one. Example 11. We've got 16 square root 5 to be divided by 2 square root of 4. Now that looks like this only simple thing we can do is 8 and the square root of 5 over the square root of 4. But when we come around the side, notice that 8 is also can be written in terms of the square root of 4. So we got 8 is the square root of 4, which we know, sorry, no, this one's easy, sorry. Square root of 4, of course, is 2. So that's 4 square root 5. Yeah. So you might want to just go straight into number 6 for that section. And last part 7.